Hello, my name is Todd Evans and I am a Level 2 Product Support Engineer at Cole Morgan, and this video series is an introduction to the AKD Ethernet IP servo drive. Welcome to video 9 of the AKD Ethernet IP video series. In this video we will discuss the diagnostics that are built in to the cyclic data. Once general motion is accomplished, for example using the AKD home, AKD jog, AKD move, add-on instructions, etc., the next question customers usually ask about is how to monitor feedback position, status, faults, and other diagnostics. Some of this information is already accessible and built into the cyclic data when the axis is declared. This includes status words 1 and 2, drive motion status, and actual position and velocity. Below is a snapshot of the response assembly data structure from the AKD Ethernet IP communications manual, and I've highlighted the bytes that is related to some of this information. Status words 1 and 2. Byte 0 and byte 2 of the response assembly consists of status words 1 and 2 respectively. The top left screenshot shows the response assembly structure, and I've highlighted the two status words. This comes from the AKD Ethernet IP communications manual. The bottom left screenshot shows the bit descriptions of each bit of each status word. The right screenshot shows the axis underscore internal dot status group and bits under that group, which is updated by the AKD drive add-on instruction each scan. In this way, this naming convention, let's take general fault for example. Well, axis underscore 1 dot status dot general underscore fault. That naming convention is intuitive and a lot easier to understand than if you were to point to axis underscore 1 dot input dot data. Actual position. Bytes 8 through 11 of the response assembly contain the current actual feedback position from the drive. In the top screenshot, we've highlighted in the response assembly structure the bytes that contain the actual position data. The bottom screenshot shows the current value of the axis underscore internal dot position feedback, which again is updated by the AKD drive add-on instruction each scan. This allows the position feedback to be displayed as a double integer instead of 4 consecutive bytes as it would be in the axis underscore 1 dot input dot data, and hence is more intuitive. At the time that this snapshot was taken, the drive had been homed, the units of the AKD Ethernet IP drive in Workbench was set up so that Workbench units was equivalent to Ethernet IP counts. The drive was commanded to go 10 revolutions, and the feedback position after that move
actual velocity.
655.
Bytes 12 through 15 of the response assembly contain the current velocity feedback. The top screenshot shows the response assembly structure and highlights the bytes that contain the actual velocity data. The bottom screenshot shows the axis underscore internal dot velocity feedback, which is updated by the AKD drive add-on instruction each scan. This allows the velocity feedback to be displayed as a double int instead of 4 consecutive bytes as it would be in the axis underscore 1 dot input in this case. Motion status. The drive motion status information in bytes 16 through 19 of the response assembly is the same status bits contained in the drv.motionstat parameter keyword. In the top left screenshot, it shows the bytes for the motion status in the response assembly. The top right screenshot shows the axis_internal.input.data location for the current values of the data as read by the AKD drive add-on instruction with each scan. The bottom screenshot shows a portion of the drive.motionstat bitwise descriptions from the workbench help. It is up to the programmer to copy this data from the axis_internal.input.data of the structure to the ladder and to parse this data in their PLC code. Or, as an alternative, use the AKD motion status add-on instruction. This differs from the previous slides in that the drv.motionstat is not a subgroup of the axis internal structure as the status, position, and velocity feedback were. Diagnostics adding status to the ladder. Sample project demonstrates how to access some of the information in the response assembly for a given axis. In the screenshot from the sample project here, you'll notice that on the left there are status bits that come from the structure, and they are passed on the right to individual coils on each rung so that these coils or status of the coils can be used elsewhere in the ladder. Note that the status comes from the structure axis_internal.status.x, where x is the given status bit description. In the case of the sample project, axis_internal name is axis_1. And if you look, for example, in rung 3 above, the axis_1.status.general fault is taken from the structure. It's updated with each scan using the AKD drive add-on instruction. That contact, when true, is passed and turns on the coil is axis faulted. The is axis faulted state, on or off, can be utilized elsewhere in the ladder. Review. The rungs that were aforementioned above reference status bits under the declared axis_1 from the controller tag database. For axis_1, you can see the screenshot below. Note the full 64-byte command response assemblies axis_1.output and axis_1.input, as well as the dot position feedback and dot velocity feedback, are available from the controller tags that we've just previously reviewed. Expanding the axis_1.status, the following information is given. Again, we covered that previously. Just remember the structure depends on the AKD drive and instruction to update the structure's data every scan. Likewise, note if the ladder needs access to actual position feedback, for example, the axis_1.position feedback can either be used using that tag or copied to another tag. In the sample project, we show a copy block, and it's unconditionally tied to the left rail, and the source is from the structure axis_1.position feedback, and it's copied to a destination axis_1_current_position. And then that tag, as you can see when you hover the mouse over it live in RSLogix 5000, you can see the data type, and you can also see the current value. And at the time this was taken, the value of the current position was 19,466. Read a parameter. The sample project demonstrates how to read a drive parameter using the AKD get parameter add-on instruction. Keep in mind, if you need the status of a parameter while other add-on instructions are executing, such as the AKD move add-on instruction, for example, then you may want to use another method such as an MSG block or dynamic mapping. Dynamic mapping or other parameter access methods will be covered later in the series. But one of the key points here is that when you're using
the AKD get parameter, AKD set parameter add-on instructions that no other add-on instruction can be executing at that given time. Hence, potentially one of the caveats of using these add-on instructions. In the sample project, one of the examples of using the AKD get parameter is to access a read of the drv dot disable source. Below the rung, note from Appendix B in the Ethernet IP communications manuals, there's a list of drive parameters and their instance values. In this case, the drv dot disable sources is instance 121. So if you look at the AKD get parameter add-on instruction in this example, the parameter number is 121, and then a parameter tag, to hold the parameter value anytime this add-on instruction is triggered and executed and complete. It will hold that value at the time of the read. The AKD get parameter and AKD set parameter add-on instructions are limited to double integer data or 4 bytes. Also, in the case of dynamic mapping, which we cover later, using 64 bits or 8 bytes consumes more bytes of your command and response assemblies. In order to facilitate a 4-byte access to these parameters, instances were added and bug fixes, such as writing a negative number, were resolved in the firmware beta release of 1.17.3.0 in February of 2018. And these fixes are in production releases after that. The 32-bit instances can be used for the AKD get parameter or AKD set parameter add-on instruction to read or write to from a parameter. In the screenshot below, if you look at under communications, Ethernet IP, in the response tab, for example, you'll notice that's highlighted the home.distance. Instance number 199 is the 8-byte version, and instance 200 is the 32-bit or 4-byte version. Here's an example of using the Workbench GUI and the dynamic mapping list as an instance lookup table. In this case, I'm not actually mapping the instance, but I'm using the GUI to look up the ID or instance number. If, for example, I wanted to use the AKD get parameter add-on instruction but need to look up the instance number, this is a convenient method. There are also a list of instance numbers and drive parameters in the appendices of the 2 AKD Ethernet IP manuals, but currently the 32-bit versions are not listed there. Again, below is the 2 versions of the home.distance DIST, the 8-byte and 4-byte instances as an example.